Okay, let me start. We had last time discussed the action and an action principle. I've shown how the Einstein field equations can be obtained by varying an action. And there were several questions that were raised during the last, or actually after the last lecture. And this is why I would like to spend the first half hour roughly, or maybe even the full first part before the break, to discuss a bit more aspects of this, of the action principle. I think you were right in saying that I glanced over some calculations, and this is true. At the end, I introduced the action for an electromagnetic field, and then I said, oh, if you take the variation, or if you apply the variation principle, you get the energy momentum tensor corresponding to this field. And I said, okay, there's some calculation in between, and many of you were apparently not satisfied by the fact that I haven't shown this calculation. So we'll do that now. But before starting with that, let me briefly give you an overview where we stand. So what we have done first, before we went to the action principle, was that I just stated the Einstein field equations as a postulate. And this is sufficient for applications. And actually this week, in today's and tomorrow's exercise classes, you will be asked to derive the Schwarzschild solution from the Einstein field equations. This is the solution you can obtain as a vacuum solution, because actually you're only solving the part where there is no mass outside of the central mass, if you like. And you impose certain symmetry conditions. So actually the Schwarzschild solution is the unique static and spherically symmetric solution in vacuum. And of course it's parameterized by the mass that's inside, but the point where the mass sits, it's actually the singularity in time, as you know, but let's say the space-time point where the mass sits is not part of the manifold that is covered by the solution. The solution covers everything around. And this is very much like the Newtonian potential. If you write down the Newtonian potential of a point mass, what you get is 1 over r, but 1 over r is of course diverging for r equals 0. So strictly speaking, the point mass itself is not part of the domain of space to which the solution applies. And that's very much the same for the Schwarzschild solution. So it only covers the vacuum part, the part around the actual matter. But then by appropriate boundary conditions, you still get the mass inside. So specifically, the way this can be done in GR is to say that we already know how the gravitational field should look like very far away from the center, because there it's like in Newtonian gravity. That's what the experiments show. I mean, the experiment agrees with Newtonian gravity when we are far away from the center. So we can just start with essentially this mass as a free parameter, and then at the end match it so that it gives exactly the field we would expect to have at a certain distance in the Newtonian approximation. And that's the and then of course the solution applies everywhere, but this is essentially the point where that you use as a reference to fix the mass. You go very far away from the source and make sure the solution agrees with the Newtonian solution. So that's one of the ideas that we will see today in the exercise classes, or see and apply. Okay, so that's things we can do with the Einstein field equations. We will also today in the second hour see that the Einstein field equations can be used to derive other vacuum solutions very easily. For example, the vacuum solution that is relevant for detecting or for understanding gravitational waves. To actually solve the Einstein equations in a scenario where you have matter. So for example, you want to look how does a gravitational wave actually, how does it emerge from rotating black holes? That's an extremely difficult problem that can never be, today it cannot be solved analytically, and for that we need numerical techniques. And I mention that because there will actually be a special tutorial like last week again this week, namely on Friday at 4 o'clock by Eleanor Hamilton, and she will talk about some of her research. She herself does research in the area or in this field that I just described. They try to understand what's essentially the radiation coming out from certain objects, from real objects we have in space. And that we need to know when we want to detect gravitational waves. We of course need to understand what we are looking for. We'll just see some waveform, and we need to understand, does this waveform actually match some source? And so therefore this is an important part of this big effort that is currently going on to understand the universe in terms of the gravitational waves that we are receiving, which is an effort that has just started recently with the first detection of gravitational waves. And that's something I will discuss a bit in the second hour today. But then on Tuesday, what a main goal was then to take a step back and ask ourselves, how can we understand the Einstein equations on a more fundamental level? Is there an even deeper principle from which they arise? And it's now questionable what is really the deep principle. Is it just the Einstein equations themselves, or is it something else from which they can derive? And we had this something else, which was the action principle. And there are reasons to believe that this is really a deeper principle. And one reason for that was that we could derive other things from that principle. So in particular, we also get the Maxwell equations from the very same action. And that's a part that I would like to explain. I will not derive the Maxwell equations. That will still be part of electrodynamics, but I will talk a bit more about the action that enters there. Okay, so if you remember, last time we introduced the Einstein-Hilbert action. I should really call it Einstein-Hilbert and not HS. Okay. I think, yes, I called it. I think I didn't use these indices or these superscripts last time, but let me nevertheless do that. Last time I had a subscript which was indicating over which region in space we are integrating. I will just drop that to not make the notation too complicated. But the idea is, of course, that an action is usually arising or defined by an integral over space. And the fact that I drop the integration region doesn't mean it's not there, but it's just implicit. So that's the action. Now, from this action, we were able to get the Einstein equations in vacuum. Then I said we have another action that we could define, which is the action of the electromagnetic field. I call it SEM. And this action depends, of course, also on the metric, because the electromagnetic field is embedded in space-time, and we need to tell it what the space-time is. But there is also the vector potential and capital A that I mentioned already last time. So the degree of freedom of the electromagnetic field is essentially captured by this A vector. And actually, if you think in terms of an action principle, we have a priori, if I write this action principle, you may ask yourself, what is really the variable with respect to which we are varying? And indeed, I even wrote the action itself, or the Lagrangian density, in terms of the electromagnetic field tensor F. Let me write it down again. It's essentially a product of two such Fs. I mean, it's the same F, but the indices are different. And I told you the F is just an abbreviation for the exterior derivative of A. Now note that I wrote here an A, which means that I'm considering, or I'm regarding the action as an action which is a function of A and not as a function of F. So I could as well have written an F here, but that would mean something different. It would mean that if we now vary it, we would vary with respect to F. But F has more degrees of freedom in principle. So here, by actually taking A as the underlying degree of freedom, we make a choice. And you can ask, why do we do it like that? At the end, the ultimate answer is we get the right thing. There, of course, I mean, we get electrodynamics as we know it. And so the action principle is really something that is postulated. And then, of course, you justify the postulate by comparing it to experiments. And the postulate really is that we write an action depending on A. So in that sense, A is the fundamental degree of freedom that is considered in this action. And then we write it with this F just as an abbreviation. So it's just, I could as well have written here a DARS and DAMN. And the reason why this term looks like that is, again, it's a postulate which is then verified. However, there's a lot of guidance we have, because what you know also for this thing here is that obviously the action should be something that is at the end coordinate independent. So the action, the left-hand side, is just a number which depends on the integration region. But once we have an integration region fixed, which we can do without referring to a coordinate system, we just get a number. So that's at the end a number coming out of this big integral and so on, but it's a number, and this number should have a physical meaning in the sense that it's not influenced by our random choices we make, by saying, okay, we take this polar coordinate system or this, let's say, Kruskal-Zekeres system and so on. So this seems to be a trivial statement. It has to be coordinate independent, but this actually imposes a lot of restrictions. There are not many scalars you can get from that somehow involve the metric. So R is, of course, something that is derived from the metric, which, I mean, the scalar is coordinate independent. So if I give you the metric and ask you, can you somehow define a scalar that depends on the metric and its derivatives and so on, but it should be a scalar that is independent of coordinates. Then you will find out that there are very few things that you can do. There are actually mathematical statements about that, which I will not discuss in this lecture. But the point is, you have actually not so much freedom here. Of course, you could say once you have a scalar, you can take, for example, the square of this scalar or 7 times this scalar. That is still allowed. By the way, if you just scale it up with a constant, that of course has not a big influence. You can just absorb the constant here. But if you take the square or the square root or maybe a polynomial of it, that would be a different action. I could also add a constant to it, and this will actually be the term that would lead to the cosmological constant that I will discuss next week. So one other scalar, which is in a way trivial, is to say, instead of R, the Ricci scalar, I just put a constant there. And of course, a constant is in particular scalar. And it's still a non-trivial thing, because this constant is somehow integrated over the volume form. So the action would just measure the volume. So the action would be essentially the volume if I put here a constant. And so that's another allowed thing. And indeed, it led to something that is probably physically there, which is this cosmological constant term that we also saw in the Einstein field equations. For the moment, we will not consider that term, but I just note here that we could add it to the action by adding a constant there. But then there's really not much else that you can do that depends on the metric and is still a scalar. And in that sense, theoreticians have not arbitrary choices. It's hard to count because you can take polynomials, but the degrees of freedom you have to even make a postulate before you have to go to an experimentalist and say, now I want to see whether this postulate really corresponds to how nature is. The degree of freedom is already reduced enormously by just requiring that it has to be a scalar. Note also that this R, like the F here, is just in some way, you could say, an abbreviation. In principle, this is a function of G. So we are varying with G. We are not directly varying with respect to R. That would be another postulate. It would not lead to a sensible equation. So the postulate is, this is the action, but the action should be understood as an action which depends on G. And we vary with respect to G to get the equations of motion. Okay, now I think I discussed this a bit. This was a bit short, maybe last time. So what did we do? I still want to summarize that briefly. We took the Einstein-Hilbert action, took the derivative with respect to the metric, And you know, I had this notation. Sometimes people would here just write only delta S, E, H, but this notation really emphasizes that I'm actually taking the derivative with respect to G. G is the only, I mean, this whole action only depends on G, so there's not much choice, but here, obviously, it makes a difference whether I vary with respect to G or with respect to A. We calculated that, and the calculation, I'll write down the result, for later use today, gave again this prefactor which was essentially not affected, and then we found in a very long calculation, which I think filled almost the whole lecture on Tuesday, we found this result here. Okay, so that's what we have already. That was all the work that came out of all the work we did already. But now there was another part which I only mentioned. And this was the part where I said, let's now take the electromagnetic field action. And if we also take the derivative with respect to G, then we get the matter part of the Einstein field equations. So here, of course, this part is what is usually on the left-hand side. It's the geometry part of the Einstein field equations. And this will give us the matter part, the electromagnetic energy momentum tensor. And that's the part that many of you asked me to actually derive. So, and this derivation is much less cumbersome than the one here. I could actually do it maybe in 15 minutes, and I would therefore like to do it here. So let's just do it. It's useful in order to do this derivation to first note that we can take the derivative inside of the integral. So that's something we already did last time. I think I didn't discuss it in detail. I just said we always assume we can do these things, and I will also do that now. But you know, in mathematics, you have theorems that tell you what are the conditions for functions that allow you to essentially exchange integrals and derivatives. And here we will just again assume that all the functions are such that we can do this. So I will take this derivative to the inside of the integral. I still have the same integral with the electromagnetic field tensor, and I will now write it in terms of coordinates. This will not change anything here. I still have this tensor, but instead of the volume form omega g, I will have again the square root of the determinant of the metric. And then I also somewhere need this delta g, and then the integration dx4. So this is the coordinate expression for the action. Now, this is still a kind of abstract way of writing it, because I just said, let's take the derivative with respect to g, but g is a tensor itself. Now, this is well defined, because the derivative with respect to a tensor gives kind of just the corresponding dual tensor. It's like if you take a scalar and you derive it with respect to a vector, you get a covector. And the reason is just that if you again multiply it or put in the vector, you get again a scalar. But here, because we want to work in coordinates, I will now put here, I want to do the derivative coordinate-wise. And then I need to put the coordinates or the indices both here and here in the variation again. So these cancel. So in some way, you could understand the expression I had before I put these I and j's as actually meaning in coordinates that I take it with respect to all these coordinates and then do that. Without coordinates, I could also express it as a trace. Trace means I take the tensor and sum over the coordinates. Okay, so that's essentially what the derivative means. So if you ask yourself why is it exactly like that, then please go to the explanations I gave on Tuesday, where I essentially told you that this type of derivative that we described here is analogous to just taking gradients and so on. And if you look at things in that picture, then it will be very clear why we do that thing here, why we can put indices like that. Okay. Now, the other thing I told you already on Tuesday is that this type of derivative with respect to functions also satisfies all the rules that you know from derivatives, in particular the product rule, which we need to apply because we have here a product of 3 different g's. So we better apply this to each of them individually and sum it up. So let's do that. So if you apply this derivative to gij to the first occurrence of g, which is grm, then what we get is something very simple. I mean, you see, what is g derived with respect to g? Now, by the way, I made a choice by actually saying we take the derivative with respect to the metric with indices upstairs. I could as well have done it with indices downstairs. I just need to be consistent here and here. This doesn't actually matter. It's just that already last time we did it with respect to indices upstairs. And if we take the derivative with respect to something with indices upstairs, we get something with indices downstairs. This was exactly what we got here. You see, because the whole thing still needs to be a scalar. And of course, taking the derivative means we are essentially determining the thing which has the property that if we combine it with this, gives again a scalar. But what does the object need to be that combined with this gives again a scalar? It needs to be the corresponding cotensor. So if this is a 2-0 tensor, then this needs to be a 0-2 tensor. But it would just be the opposite if we put here a gij with downstairs, then we would have here indices upstairs. Nothing would change. It would be the same thing. And indeed, you know, with the metric, we can always raise and lower indices. We could just essentially put the metric which raises the indices here and at the same time lowers them here. So it's really the same expression. Now, if I take the derivative of the metric with respect to itself, I just get a delta function. Actually 2, because I have 2 indices which need to match. So I get this result here. And the same is, of course, also true for the second term in this product. I will just get a corresponding delta function. Then the third term is a derivative with respect to the metric of the square root of the metric tensor, of the determinant of the metric tensor. And here I just used the result we derived last time. So I'll just copy it from the lecture on Tuesday. And if you look up on Tuesday, we had exactly such an expression. And I think the result was like this. Okay, let's briefly check that. This is the Tuesday lecture. I think we did this somewhere. Yeah, I think here you see it. We took the derivative of g, and so we got this type of expression here. I think we have even a better, oh yes, I think here is even a better expression. You see it from here. Okay. So I didn't put the delta now in, there's always, I mean, at the end we will have to multiply with this, of course. And we just need to remember that. So let's do that now. So I can now just put all these things together. So the reason why I wrote down all these terms is that I essentially wanted to take the derivative of the product of these 3 terms. So let me write this down. So it was the product of grm, gsn, and the square root of the determinant of g. And now what we found is that from the first term, we get the delta function, which I just copy here, jm, and then it doesn't affect the other terms, so the gsn just remains. And the square root I will put at the end outside of the bracket. Then from the second part, okay, I think I will need more space here, so let me put this down. Okay, so the second part, you see it's still here on the right-hand side. I can just take it from here. So the second part just keeps the grm, then has a delta function. So the corresponding delta function here is, of course, analogously just delta Si and delta Nj. And then from the third term, we got a -1/2 Gij times the square root of the determinant, which we have from every term. So I just put it here. I think I forgot. Okay, I think I forgot something. The last term, of course, is not alone here, just with the G. That was wrong. So here it still has, of course, the previous factors, which I need to insert. And the previous factors were just GRM and GSN. Now I think the expression should be correct. Okay. Now the goal was, of course, to get this whole integral right. So let's see what the total thing here is. So we wanted to have this. Let me call this star. Now I scroll up, but you still see it on the right-hand side here. Let's see what this integral, or not the full term in the integral is. Okay, so what I need to do to get from here to the full star is just to multiply it with FRS and FMN. But what happens if I multiply the first term with FRS and FMN? So these delta functions will, of course, now set in and do their work. So what do they do? So first of all, I get, of course, an F, which a priori had an index R, which is turned into an index I. That's what the first delta function does. Then what happens with the index S of the first term? The index S is raised by this G here to an N. So I can just instead write an N, but upstairs, because that's what the G does. It raises indices. And then I get to the second term. F, the next F has an index N, first an index M and then an index N. The M is just turned into a J, and the M, what happens with the N? I think nothing. We can just leave it. So, because I could, of course, raise it to the S, but I can only, you see, I can only apply this once. I've already used this G to raise the index that was here down, up, and now I can no longer apply the G again. But you see, there will anyway be a sum over N. So that's nice. So this N will be, these two N's will be contracted. Now for the second term, I can just do it analogously. So let me do it a bit faster. So I have the index F R, which will be, okay, an M will, okay, still need to be careful. It will be an M, and then the next term, the S will be turned into an I. Then from the other F, the N will be turned into nothing. It will just stay there. And the last index will be turned into a J by the delta function. Okay, now we're almost done. Now I have still this -1/2 term of the whole sum. Here you see what the G's do. You can just regard these two G's as acting on the first thing and raising both indices. One raises the R index, the other one raises the S index. So I get F, M, N. The raised indexes are M and N. And then I still have the other F on which I no longer act. The other F just had M, N. And then I still have G, I, J. Okay, I think that's it. We still probably need to put somewhere this, yeah, okay, the square root of the determinant needs to be still there. So let me see whether I can make some space here. Okay, so the whole thing still has to be multiplied with the square root of the determinant, which I can write in the coordinate independent way as omega g. You know that this was the same essentially. Okay, maybe that's too early to do it now because it's still not in the integral. So let me just write this. Okay. But now we can do the full action. Now we have the star, and the rest is just the integration over this. So what we wanted to have, our goal was to have delta S derived to, with respect to G. And now what is our result? Yes, so so first we have a prefactor of -1/4. But note that the first term here, fin, and then the next one is actually identical to this one. The way to see this is that to remember that the electromagnetic field tensor is antisymmetric. Why is it antisymmetric? You know that it's actually obtained from as an exterior derivative of a one form. A is a one form, and you took the exterior derivative, and the exterior derivative again gives a form, a two form, and the form is always antisymmetric. So if I change the order of the two indices, I get a minus sign. If I do the same here, I also get a minus sign. But note that if you change the order of the indices in both the first and second factor here, then you get exactly the same as here, except that the summation index was called m instead of n, but that of course doesn't make a difference. So we essentially have twice the same term. And I can absorb this, so the prefactor was -1/4, but now I just put 1/2 because I have twice the same term and only write the term once. So I'll write it here, in fjn. And then I still need to put the other term. Now, this other term had already a 1/2 in front, so I don't need to do anything here. I'll just write it as f mn gij. And then now I can finally put my volume form. So there's still the delta G and the omega G. Now I hope at least that this corresponds essentially to the electromagnetic field tensor Tij. So let's see, I think I mentioned that field tensor already last time. Let's see whether we had it somewhere. Okay, I see. Okay, there still seems to be, okay, it should be this one here. Now I see that there's probably a minus sign, a 1/4 here missing. Okay, let's see. Somehow I'm missing a 1/4. Okay. Okay, so let's see. I need to somehow identify where I lost the 1/4. Aha. Okay, I think I made this here wrong. So here I already had the 1/2. Okay. Where is the 1/4? Okay, let me check again what we should have. We should have a 1/4 in terms of the FMN. Okay, does anyone see where I missed the 1/4?
Yeah,
so somewhere
the people saying that you have the 1/4 in front of the whole integral at the beginning.
Oh,
then you kind of insert it in the first term, but not in the second.
Right. Oh, yes, right. Okay, I forgot it from here. Right. I took it into account when I put this because we had the factor of 2, but I didn't put it in the next one. So we still have the 1/2. Okay, yes, I see. We have here the 1/2, but we have an additional 1/4 from here. So we have still a 1/2 here. So we need a 1/4 from here. Okay, thanks a lot for the help. So now we have the correct tensor. And you see this 1/2, this comes now in from the definition of Tij that I also gave you last time. I said, if we make a variational principle, and I'll briefly go back to this thing. If you have a variational principle, a general one, some Lagrangian density, which is now a concrete one in the particular case of the electromagnetic field. And we take this derivative with respect to the metric, then what we get is something of this form, and we define the Tij with in terms of this equality. Now, if you look at this equality, this also has a -1/2 in front. So whatever is in the integral in front of the variation has to be the electromagnetic field tensor. So this is indeed then compatible with this general definition I gave you. Okay, so what have we achieved up to this point? So let's see. We have two derivatives, and the idea is now that the total action, let's call it S total, of a physical system. That the physical system could now be, let's say, a universe which only has, let's say, geometry. So the geometry part is covered by the Einstein-Hilbert action. And then, let's say, in this universe, we also have electromagnetism. So we have, in addition, an action that says we have some electromagnetic field. And now in this universe of just these two actions, we get dynamical equations. Of course, we could now add more stuff. We could say, no, we want to consider not only a universe with only electromagnetic radiation, we may also want to put more stuff here. So we could, for example, have something, an action for particles, for example. But let's, for the moment, just suppose we have a universe where we only look at electromagnetic radiation. We think the rest is negligible. Then, of course, the variation of the total action with respect to G gives now, I mean, by linearity, we get the variation of the Einstein-Hilbert tensor, or the Einstein-Hilbert action. And we already saw that the variation of the Einstein-Hilbert action gives us this 1/16 pi g Newton, and then the whole stuff with the curvature, Rij minus Rgij. And then the integral has the volume form and so on. So there's still a delta G that I may need to put here. But then by linearity, I can also take the second integral into this very same, into the same integral that I'm writing here. And so this integral is that part here. So what I can do is I can put here, okay, there's a -1/2 because I add everything up, times the Tij. That is also figuring this integral. Actually, I should be careful again with the prefactors. So let me put it like this. The 1/16 Gn only applied, of course, to the first action, to the Einstein-Hilbert action. So that had this prefactor, and the T only had the prefactor -1/2. And we integrate over all that and vary with respect to G, and the integration is over the volume form. So that's our total variation. And now we require, the equation of motion is now to require that this should be 0. So that's a requirement for all variations G. But of course, if this is true for all G, so maybe I should write here for all delta G. That's important that it has to be true for all delta g's, but this integral can only be 0 for all delta g's if this term is 0. Otherwise, if it's somewhere non-zero, you just choose the delta g to be positive exactly where this thing is non-zero, so that the whole integral becomes positive. That's the usual thing that you probably know from classical mechanics. So we immediately get, as a result, that this term is 0. And I'll just write this down so that it's really clear what I'm doing here. Minus 1/2 Tij has to be 0. And that's, of course, equivalent to the Einstein field equations. I just need to multiply on both sides. I mean, first I put the t on the other side of the equality and multiply everything with 16 pi gn, and then I get the Einstein field equations for matter now. So now we have really done the full job. We have not only derived the Einstein field equations for vacuum, we have now derived it, at least for the example of electromagnetic radiation, also for matter, where the matter is the electromagnetic radiation. Okay, so one may now briefly come back and ask oneself, why is this more fundamental? So first of all, one answer is that this equation here is, of course, somehow simpler. I mean, you can forget the prefactor. That's just the prefactor. That has no significance. You could absorb it into constants. That thing is certainly simpler than the actual expression that appears in the Einstein field equations, which is the rigid tensor and so on. And this is also simpler than T. You see, the T is that. But that's not really the reason why we are so much interested into the variational principle. The real reason is that it's much more universal. And what I mean by that is you can now take the same action, I also mentioned that last time already, and take the derivative with respect to A. So I do the very same thing, but I vary with respect to A. Of course, I could also take the total action and vary it with respect to A. That doesn't make a difference because the first part of the total action doesn't depend on A anyway. And then I could also require that this is 0. So that's now a completely different requirement. Before I took the derivation with respect to A, and what we get, and this is now a calculation in electrodynamics. And I will not do it here, but you probably have done it in electrodynamics because you take just a derivative with respect to A and not G. So G has a kind of passive role. And what you get is an expression which looks like this. Of course, in electrodynamics, you were assuming that the underlying geometry G is flat. If you're not doing that, but repeating the calculations, you get the very same result as you would get in electrodynamics, except that there is here, instead of a comma, a semicolon, indicating that you're actually taking a covariant derivative. I'm now just for the moment assuming that you have seen that in electrodynamics. And indeed, in electrodynamics, this thing here corresponds to the, maybe I'll write this here. Star corresponds in flat space-time, because electrodynamics was in flat space-time, to the inhomogeneous Maxwell equations. You may now ask, why are they inhomogeneous? Because they are equal to 0. So what are the homogeneous equations? Just as a reminder, this is really now not part of GR, but the homogeneous equations are essentially the equations that df is equal to 0. Why is this true? Remember that f was itself the exterior derivative of A, and twice taking the exterior derivative is just always equal to 0. That was one of the rules that we have seen when we discussed the exterior derivative. So the homogeneous equations, okay, these ones here, maybe I should write here, these are the homogeneous equations, the Maxwell equations are those. These are essentially some equations that are already implicit or that are automatically given by the fact that we just work with the vector potential. So they don't appear as equations, but if I still want to have them, I can say, okay, we know that this is 0, and that would mean if I started with f that df is 0. But if I start with a, then there's no equation to be enforced. So I only have the inhomogeneous ones. Now you may still be unhappy and say the inhomogeneous ones should somewhere have a charge. I mean, the right-hand side is here 0. And the reason why it's 0 is because I just said before, we are looking at the universe that only consists of the geometry and an electromagnetic field, but no particles. So to actually get something on the right-hand side, I would have to go back to the total action. So, and remember, the total action was the Einstein-Hilbert, of course, plus the electromagnetic field. And now I would have to add another action, something with particles, or some interaction between particles. I could write it like that, interaction between electromagnetic field and particles. So I would have to add that. And what could that be? How would that look like? It could be some integration, for example, which takes A. And remember, A is a form, so it eats vectors. And an action always needs to be a scalar. So I somehow need to turn it into a scalar. What would be a natural thing to turn this covector, this form, into a scalar? What should I feed it with? One natural thing to feed it with is just to feed it with the current. And remember, we discussed a week ago charge and currents of charges. And this was a vector. I emphasized that very much, that charge is not just a density, it's, I mean, a scalar, it's a vector. And that's, of course, very suitable to feed it into A. So I could just postulate that a reasonable action that somehow captures how particles, how charges interact with the electromagnetic field could be that. And it turns out that this is indeed a good action. If you, again, take now the derivative of this with respect to A, what you get is exactly what you would kind of expect here. You would, on the right-hand side here, get the Q. I mean, that's almost obvious already. I mean, if I take the derivative of this with respect to A, obviously I just get the Q, and the Q is what should be here. So everything now comes together in a very nice way. You see, everything can be obtained from action principles. Of course, these still need to be postulated. Now, of course, if I introduce charges, these charges themselves need an action, because I don't want to know how do the charges themselves evolve. So I also should then take the derivative of this with respect to, for example, G. I mean, okay, this is not a new action. I just take this action and take this with respect to G, or I can take this derivative of this with respect to Q. And this gives me the state, the evolution equation for the charged particles themselves, which would be the Lorentz force. So again, I get everything from the same thing. I take this, instead of varying now with respect to A, as we did so far, we would now vary with respect to the new degree of freedom we have, which is the particles which are characterized by Q. So I take the derivative with respect to Q, and I get the Lorentz force. And maybe you remember at the very beginning of the course, or also in the middle again, we said that if you just have particles, particles move along geodesics. This can now also be understood in the context here. We could just add another action to this and say we also have just particles freely moving, not charged ones. We just put an action which is essentially the action that we already considered, which is an integration over, if you remember, I mean, it was an integration of G of the velocity vector of the particles, v, and then along the particle path with respect to some parameterization lambda, and here a square root. That was an action. So that was a particle action. You could add that as well. And now if you if you take the derivative of this action with respect to gamma, to the trajectory, you get the equation of motion for the particle, which is the geodesic equation. If, maybe I'll write this briefly down. So if you take the S particle with respect to the gamma, you get geodesic equation, which is of course the equation that if you take the derivative of v with respect to v, this would again be, this should be 0. So that's the geodesic equation in short form. What happens if you take the derivative now of the particle with respect to g? Then you would get again the part of the matter part of the Einstein field equations, but now for matter which really is particles. So I would get kind of the matter part of the Einstein field equation, which is of course just the T, the tensor Tij for matter, for particles. So now we can really do everything. I will not do all these calculations. I think we are now done essentially with calculations. I think I explained it now with an example. We have at least done two derivations. We have done the full derivation that leads to the Einstein field equations. And I just mentioned and refer to the lecture notes that if you take the derivation with respect to A, you get the Maxwell equations. And I also just claim now, and you're free to verify that I can, for example, add such actions and so on, and I get always the corresponding equations that you already know from the particular field. So I could now take, go into particle physics and add an action from there, and I would get the corresponding equation of motion for that type of particle with its own interactions from that term. But I would also, by taking the derivative with respect to g, get the corresponding influence it has on geometry, meaning I would get the corresponding electromagnetic field tensor. So I hope, well, to now conclude this, let's say, interlude, I hope this at least clarifies a point I made last time. And the point I made last time was that, this is now the other notes from last time, that we can generally define the the energy momentum tensor in terms of an action, which is more natural. So rather than just somehow constructing T, which we did for particles, we just say, let's take whatever action we have. You invent some action for a particle that you find, maybe you detect a new particle, the Higgs particle, let's suppose you find the action that describes this particle, and now you need to know how does it influence the gravitational field. What you do is you take that action, but instead of taking the derivative with respect to the whatever degree of freedom that this new particle has, you take the derivative of this action with respect to g. That's what you're doing here, and then you get the corresponding t defined via this variation. So this is a very generic way to, for any type of particle you ever will detect in the future or have already detected, to derive the corresponding ingredient to the Einstein field equations, which is a non-trivial thing. It's not as trivial as in Newton, where you just say we need to know its mass. Here we really need to know the full tensor, but the way to get it is from this action principle. Okay, now I am again a bit over time for the break. Let's now make a break, and then I'll restart maybe at 1:05. Are there any questions now?
There was a question in the chat. Oh,
it's mine.
Yes. Okay.
So I'll just ask it directly. So I was just wondering, in the Einstein-Hilbert action, what does it like actually measure now? What does the action itself represent? If we integrate over the Ricci scalar, but like, does it have any geometric meaning that would be like interesting to think about? Or
okay, I have to admit that already, you know, if you look at the action, it has this Ricci scalar. If you remember that the Ricci scalar, how it was defined, it's somehow defined as the trace of the Ricci curvature. Now the Riemann curvature with 4 indices has a very clear geometric meaning, which we discussed. I mean, we move certain gyroscopes and we see how these things deviate. To be honest, even for the Ricci tensor, the one where you reduce it, I don't have an immediate geometric, let's say, picture of it. It's just somehow the trace of that. Now the Ricci
I think
scalars,
for the Ricci tensor, I heard a description, something like I forgot like which order the indices matter, but like if you consider like a cone that opens along one direction, in the other direction, it measures like how quickly the volume scales or something like that. It's like
okay.
in a flat space, a cone would like open linearly, and in a hyperbolic space, it would open much quicker. Something like that.
Yes, I
I saw
mean,
it in a GR.
yes, okay, maybe I should look into that. I actually tried at some point to figure out what could be a good geometric meaning of R, and or of even of the Ricci tensor, which is before we contract, because the more basic, I mean, in some way, the Riemann curvature is the most basic object. This is really what we start off with. And this is the thing that really describes curvature in a way we can geometrically understand. Then the other thing is this contraction, and maybe it has such, I mean, it's well possible that people figured out a nice meaning. I'm not aware of any, to be honest. And therefore, I cannot give you really a good geometric intuition for that. But I'll look into it again. I'm not very optimistic that I'll find something, because I also asked many of my colleagues who are actually experts in GR, and I have never heard a really satisfactory answer, at least not one that satisfied me. So unfortunately, I don't think I can give you a good answer or a good geometric picture. Now, of course, an action, generally, if you think of it in terms of like how you're used to it from mechanics and so on, has a mean, I mean, you can kind of try to translate it to the meaning you have from there. So an action is somehow the energy times time and so on, and you could try to figure out what that means. Now, I think I mentioned already last time that thinking in terms of energy in GR is actually highly involved business. And there are lots of debates about how should we even define the energy of a gravitational field. The problem is that normally when we talk about energy, we have the energy kind of in a I mean, you can kind of say there's somewhere in space, a region, we cut it out and talk about the energy there. But here we are somehow talking about the energy of space itself, which makes it somehow a circular thing. And there are ways to define it, but one has to be very careful one is consistent between the different ways this could be defined. And it's particularly difficult when we talk about, for example, a black hole, where the part where we would want to kind of measure the total energy is not even accessible to us. One of the problems is also that if you talk about energy, as you know, and as I explained to you, energy is somehow an observer-dependent thing. Energy is just one component of essentially a higher dimensional object, which is only then as a higher dimensional object coordinate independent, the energy momentum tensor. And therefore reducing it to one thing is also problematic for that reason. So I'm very sorry, I have not a good answer. You should really think of it as in a more, let's say, mathematical manner in this particular case, that we are just trying to see what are possible quantities that we can define, which are scalars and somehow involve the geometry in terms of the metric. And I think there are much cleaner statements. You can somehow try to use results from differential geometry to just try to figure out what is your degree of freedom. And as I said at the beginning, this degree of freedom is extremely small. So in some way, we have no choice, independently of the exact geometric and physical meaning. We are essentially forced to write an action of this type. Having said this, there are groups, and actually the group of Lavinia Heisenberg at ETH is one of these, who do research on finding alternative formulations of gravity theory. And their task is exactly that. They try to see what other tensors or what other actions could we write down that somehow make sense. And you see, this research can only make sense if you are somehow constrained. If you could write down just an arbitrary formula and postulate it, you would never get any insights because you cannot test all of those. But this research is really interesting because you have so many constraints coming from different other considerations, like the fact that they have to be coordinate independent. And there are indeed other ways to represent gravity. So some of them are just different equivalent views. So instead of working with the curvature, you somehow work with the torsion, let's say, and you try to formulate an action principle in terms of torsion. This has the impact that also the way gravity couples to matter is then different. So everything is then expressed in terms of a torsion tensor. And the fact that you can do that and you get exactly the same gravitational theory means that it's not clear that this way is kind of the physically most, or let's say the most intuitive way to do it. It was just maybe the way we are doing it. We did it historically and the way gravity was developed. But mathematically speaking, there would be really other formulations where this would look very different, but give rise to the same physics. And so if you have this freedom, you could now go back and ask yourself, what is the physically more meaningful thing? And that's what these research groups are doing. So in that sense, you could even say that finding out what this really means and what the right formulation is as a fundamental principle is still a matter of research. Okay, that was now a long answer.
No, thank you. It was interesting.
Being conclusive, but I hope it gives you some insight that there's a lot to do. So maybe that's the even better answer for future researchers. It's worth studying all that because there's still a lot of research to be done.
Actually, I'll go grab my differential geometry book real quick and see whether it says anything about the Ricci scalar in there.
Yes, if you find something, let me know. But as I said, I'm not too optimistic that there would be a very intuitive picture of that. Okay, are there other questions?
Yeah, there's a question regarding the energy momentum tensor and whether it can be somehow connected to some Noether current, or whether it can be derived from the Noether theorem. Something.
Aha, okay. So the Noether theorem, okay, I'm not sure whether the tensor itself can be derived from the Noether theorem. What you can do is the following. So you know probably from classical mechanics that if you have an action principle, like this one, or maybe the one from classical mechanics, then usually these action principles satisfy certain symmetries. I mean, in classical mechanics, for example, you had the symmetry that it's invariant under spatial translations or under time translations. And then you have learned in classical mechanics that Noether's theorem then tells you that if you have such a symmetry, this tells you that you have certain conserved quantities. And that's also the case here. So once, it's not really for the derivation of it, but once you have an action principle, let's say this one, or even the one for particles, you could say this clearly has certain symmetries. And these symmetries now, in this particular case, for example, lead to the insight, like, okay, maybe you remember that I told you when we introduced the energy momentum tensor that we have actually certain conserved things, or we wanted it to be conserved. So at the beginning, we had this conserved current, and maybe you remember that we had an expression like this. I said, if you have the current vector and we take the covariant derivative of it, this should be zero. This was essentially the law that current is conserved. So it's a conservation law. And then I told you that the equivalent thing for energy and mass is not to say that the mass current or so is conserved, but that the energy momentum the energy and the momentum as a 4 vector is somehow conserved. But this means now that if you take the covariant derivative of the energy momentum tensor with respect to one component, maybe I'll better write it like this. So then this should also be zero. So note what this means. So remember that this first index I tells you what we are talking about. If I is 0, this is the energy. If I is 1, 2, or 3, it's the corresponding direction of momentum. And the J is with respect to which direction we have the flow. So this J would actually correspond here in the upper thing to what I called I. So let me also call it J. So now this J corresponds to that. So this tells you that essentially current is, or charge is conserved. This tells you for each I, because that's true for any I, that the corresponding quantity is conserved. So these are actually 4 equations. The first one tells you energy is conserved, and the others tell you that momentum is conserved. And this conservation law can be now obtained in a similar way from Noether's theorem, starting from the insight that the action you started with had symmetries, like translational symmetries and so on. And in this case, in differential geometry, you can even say the whole thing is symmetric under diffeomorphisms. So Noether's theorem also plays a role there, and you can indeed, so you're right, you can in that sense get conservation laws, derive conservation laws from symmetries. So that's how this theorem enters here. So I now understood the question in a more general sense. How does Noether's theorem, what role does it play? I hope this gives you some insight into that. Okay, were there other questions? Otherwise, I would continue with the next topic. Julia, was there anything else in the chat?
No, nothing else.
Okay, good. Okay, then.
I have a question.
Yes, please.
So we were talking about how the when we take the derivative with respect to g, we get the contribution from the separate theory, so the electromagnetic theory, for example.
Yes.
Into the T tensor, and then you get a contribution to the curvature. But
yes.
When we take the variation with respect to A, for this complete action for both the electromagnetic and the gravitational theory, we get the usual equations of motions for the electromagnetic theory, right?
Or maybe I should be more precise, the usual ones in flat spacetime, but we get them as they correctly should look like in curved spacetime. So,
okay. So my question would have been, how do we see how do we get the back reaction from the curvature of space-time back into the electromagnetic theory?
Yes. Okay, this is a good question. So maybe I was here a bit too straight moving directly to flat space-time. So actually this is really a good question. So you're essentially referring to, for example, if I take this derivative here, so I take the electromagnetic action and derive it with respect to A and say this should give an equation of motion. So this is essentially the postulate that I have, that everything can be obtained from variational principle, and the postulate is now that if we take the electromagnetic action, we get the max, or we get whatever the evolution or the correct law of time evolution is for the electromagnetic field. Now, let's suppose you didn't know about Maxwell's theory, you would just take this derivative and you get this equation here. Now, this equation is fully general. It's an equation that makes sense in an arbitrary geometry, because you know there's this semicolon k, and this semicolon k means you take the covariant derivative. So there's implicit to this expression is the whole metric. So this expression actually depends on the metric. So this expression already includes how the metric actually acts on the electromagnetic field. And now I jumped here to flat space-time just to say that in the special case where we are now in flat space-time, we retrieve the normal Maxwell equations, which we want, because we already kind of know, also from experiments, that electromagnetism is correct. So in some sense, this is a new equation. So once you have discovered general relativity theory, you have to essentially redo all of physics in some way, because all the physics so far was derived in flat space-time. So in principle, you have to throw away everything you did before and say, let's restart and derive all the physics of particles of electromagnetic field now that we know that space-time is actually curved. But of course, the requirement is that you always, in the limit where the space is flat or space-time is flat, again retrieve what you already knew beforehand, because that was, of course, also, at least in that special case, correct. So the derivation is really, you get that, and that's the somehow, in a sense, you could call it the generalization of Maxwell's equation to the situation where space-time is curved, and therefore it automatically includes how geometry acts on matter. And yeah, the other thing is just a consistency check, whether we are consistent with what we knew so far. So it's really giving you both directions. So taking the derivative of this with respect to G gave us the direction of how does the electromagnetic field influence the geometry. So it was that direction. It was coming from the field as matter, how does it curve space-time. This derivative with respect to A gives you the other direction. It tells you now, as we have geometry, how does now how do now, for example, light rays move? That's all contained in this thing. So in some way, you could see that equation not just as a vacuum equation, which you would say in normal electrodynamics. You could see that as an equation of how electromagnetic fields move in a non-trivial geometry, and therefore how electromagnetism interacts or is influenced by the gravitational field in, let's say, a conventional way of thinking, if you would think of the gravitation as a field. So then this really includes, so this would, for example, include how gravitation bends light. This all comes from this. This would all be included because it just corresponds to solving the Maxwell equation in curved space-time. Does this answer the question?
Yes, thank you.
Okay, so
just to get back to before, yes. I quickly looked around in my book and also in the DG course from last semester, and I found a thing on the Ricci tensor in Lee's book, and I found an exercise from DG2 about the scalar curve, which I linked them both in the chat if you want to look at it later.
Okay, yes, then I'll have a look. Thanks a lot. And I'm curious to see what you can say about that. Maybe I'll come back then to that in the next lecture. Okay, let me now move to a completely different topic. We now move back to having Einstein equations now that we understand where they come from. So you should now have an understanding that the Einstein equations don't just come out of the blue. They are somehow based on a deeper principle, an action principle. But now we need to solve it. And, you know, from maybe quantum mechanics or also classical mechanics, that many things can only be solved perturbatively. So we can only approximate the solution and not solve it perfectly. And this is very much the case also for the Einstein field equations. I think Einstein, when he first wrote down the equations, thought that these can never be solved exactly. And it was actually quite remarkable that Schwarzschild, very shortly after Einstein published his theory, was already able to provide an analytic solution, at least in that case, which is exactly the solution you're going to derive in the exercises. But of course, Schwarzschild didn't have any help or hints. So you have a TA who helps you with that. But otherwise, we don't have many solutions, actually. So it's not that we could now solve 100 other things. We could solve a rotating mass configuration that would give the Kerr solution, and also one that involves electromagnetism, which would, by the way, be the one that comes from the electromagnetic field tensor as matter that we just discussed. But otherwise, I think there are very few solutions that are known. So we need to solve them perturbatively, which is not a big problem because indeed, like in many cases, we have essentially a solution that is given as an approximation, like flat one, and we just want to know how does the flat solution deviate if you have a small influence acting on it. Okay, so this is our starting point again, the Einstein field equations, and it's actually useful to somehow turn this term here, which is on the left, or move it to the right-hand side. So let me briefly do that. And to do that, we somehow can contract with Gij. So what do we get? We get contraction of the Ricci tensor with G gives, of course, the Ricci scalar. And on the right-hand side, we have the contraction of the metric with itself, which essentially just gives delta II. And delta II is just 4. and the metric multiplied with itself gives the identity, and the identity is the delta function. That's one way to see it, or the delta symbol. Okay, so we have this expression. Now t, here on the right-hand side, I just make a definition. I just define t without indices to be the contraction of the energy momentum tensor. But from this equation, I, of course, can conclude that the left-hand side is obviously just, here I have 4 times 1/2, so it's just minus r, and the right-hand side, I'll just copy. So I have an expression for r in terms of t. So therefore, I can rewrite the Einstein field equations as follows. I only have on the left-hand side the r left. So let me here scroll so that you see everything. And then on the right-hand side, I still have, of course, the factor 8 pi g. And then there's whatever was there before, Tij. But now I move this whole thing to the right-hand side. So moving this to the right-hand side just gives, I move it to the right-hand side and insert this. So I replace r with 8 pi gt. There's still the 1/2. And so what I get is this. And okay, what I have achieved now is I have an expression for the Ricci tensor, which depends on something that involves, of course, the energy momentum tensor, but also, again, the metric. Now let's just for later use, and I don't need to write this always, give this term a name. This whole right-hand side, I call it M of, and I remember that it depends on G. It's a G-dependent term. So let's now see what perturbation theory in gravity is doing. So now we make certain assumptions. So suppose you have a perfect solution, an analytical solution, for example, or for some reason you have a solution for a mass configuration, or for a matter configuration, I should say. So M stands, of course, for matter. M. So, I mean, if I give you an arrangement of planets and so on, or just a black hole, you could say, okay, this is some configuration here on the right-hand side. And now let's suppose you have a solution for that one. Of course, as I said before, we don't have many such solutions, but for example, we have a solution if the right-hand side is just one central symmetric mass. So for example, the one that gives rise to the Schwarzschild solution. So what does it mean to have a solution? It means that we have a G. So the solution is at the end a G. Maybe I should write this here. So the solution is a metric. So if you solve the Einstein equations, it means we solve for a metric and find, for example, the Schwarzschild metric or whatever it is. And so therefore we have, so having a perfect solution means we just solve the equation. We have an expression for the equation I wrote before. Okay, maybe I should call this Mij for consistency. So we have a solution for this. But now, suppose we are interested to know how the solution would look like if I slightly change the mass configuration. So, for example, let's suppose I first have just a very simple mass configuration with one central mass, and now I add a little particle to it that flies towards the mass. I could ask, how does this influence the geometry? Of course, it should influence the geometry only a little. So I'll write this down. So we are interested in the solution for modified matter configuration. And this modification should, of course, be small. I just indicate this by saying we now have a matter configuration which consists of the original one plus some delta m. So let me not put the indices. Of course, these are tensors, so I don't need to always put indices because they're just the tensors themselves. But now what we are allowed in a way to expect that this also changes the solution. So if you change the mass only a little bit, this hopefully should also change the geometry a little bit. So let's say the hope, this should change G only slightly. Change the solution. So G is the solution. G only slightly. And I indicate that by saying, okay, we should now have, we have originally G, and now with this new mass, we have something like G plus delta G. I say here hope because a priori we don't know whether it works, and it's a matter of proving theorems in GR, and that's actually what researchers do, to prove that, to find conditions under which we can do this. And actually, this is also related to so-called stability theorems, where you show that certain solutions we have, for example, the Schwarzschild solution, are still correct solutions if you don't have perfect spherical symmetry. This is extremely important to argue that black holes exist. And this was actually one reason why Penrose got the Nobel Prize this year, that he could exactly prove such statements, because one knew the Schwarzschild solution was a correct mathematical solution, but suppose the solution was really depending on precise spherical symmetry, then it would be a completely unphysical and unstable solution. So you would just say, okay, it's a possible solution, but it will never arise in reality. So it was important to argue for the existence of black holes before they were also observed, at least indirectly, to say this is actually a stable solution. And so similarly, you need here theorems to at least I mean, to at the end support that hope, and that depends on the concrete situation. For the moment, we'll just assume it works. We'll not go into these theorems. That's a matter of advanced courses on differential geometry or GR. But what does it mean to have now a solution? We have now a geometry which has changed. So it's G plus delta G, and the corresponding curvature, of course, the curvature always depends on the geometry. It's a function of the geometry. And on the right-hand side, we have the changed mass configuration, which, of course, I mean, the mass configuration itself also depends on delta G. So, you know, we saw that even explicitly here. You see that on the right-hand side. Oops. You see that here the geometry G enters. So that would still be a perfect solution if we could now solve that. But of course, we have to be satisfied with approximations. And one approximation we're making, or we are trying to make, is because G is now small. At least that's our hope. So suppose this hope now holds, that will be our assumption for the future. The right-hand side will not change much if we here change the delta G from before. So I'll just write here Rij, G plus delta G should still be approximately equal to Mij plus delta Mij. But here I just put the original G. So it's as if I wouldn't look at the back reaction, which is very reasonable to do. I mean, if I take, let's say, the Schwarzschild solution of a black hole and I put here a little mass just here, then of course this certainly perturbs the geometry a bit, and the geometry will again perturb the mass a bit, but that will have almost a negligible influence on the mass itself. It's kind of, as long as this mass is small compared to the other things I'm considering, like the black hole that is close by. Now, the other thing we are doing is we are going to make now a linear approximation of this whole equation. So, okay, okay, I don't need to write this. Let's just look at a linearized version of R. So Rij, here I really want to see the change in the geometry. I'm just saying in the back reaction, that's then again small, because gravity will then again essentially act very little back on the particles. But I want to see how geometry will change a little bit. And this change can be linearized. So that would just be the original solution. And I'm essentially interested in the deviation from that. So how much does the curvature change? And this now depends on G and delta G. So how much the curvature changes if I have a delta G, of course, depends on G. And then, but this should only be linear terms. So the idea is that this is only linearly depending on delta G. That's a requirement that I put. And then I say, of course, there could now be other terms which are somehow quadratic in G. And by saying quadratic or linear in G, I mean it's linear in G and the derivatives, and also linear in the derivatives of G. Because remember, the curvature, of course, depends on the gamma symbols, and the gamma symbols and derivatives of the gamma symbols, and the gamma symbols themselves depend on derivatives of the metric. So here, when I say the metric enters, what actually will enter is the metric, the derivatives of the metric, and second derivatives of the metric. And I will always only take linear terms in these. So I will not consider, for example, a term that where the derivative of the metric enters quadratically. That's all captured by this part. Okay, so where are we now? Yeah, we want to solve this. I mean, our goal is, of course, to solve this equation. And so, that's the Einstein field equation in the approximation. Now we could say with this linearization of R, this star can be written as I'm only looking at the actual variation. So I will get rid of the term Rij that I had before. I only look at the variation on the left-hand side, and maybe there are still these quadratic terms somewhere. And on the right-hand side, I only write down the variation of Mij of G. Why is this true? I mean, what I did is just, I used the fact that we already, and that was the crucial ingredient, we assume that we already have a solution in the exact case, which you see here on the right-hand side. So if I put in, sorry, yes, okay. Yes, I think I take this and using this, I can get rid of that term here of the Rij, because Rij, of course, this thing appears on the left side. I mean, this whole thing is just rewriting the left side. So the left side in particular includes that term here. And the right-hand side has this term Mij. But because I know they are equal, I can just get rid of both of them. So I'm only left on the left-hand side with this term plus the quadratic terms, and on the right-hand side, I'm only left with the delta. So that's what I wrote down here. So that's our new equation that we want to solve. Maybe I'll just mark it with an exclamation mark, because that's now the task. So the task is, in perturbation theory, solve this for delta G. So the G without the delta is already given. Remember that. That was the solution that we are already starting off with. And now we are asking about the perturbation. Okay, so that's really very similar to what you know probably already about perturbation theory in general. So we are somehow trying to start from a known solution and change it a little bit. What you have to note here is that the thing we are changing is the metric. So we're changing the metric a little bit, and depending on how we changed on the right-hand side, the mass configuration. But there's now one maybe somewhat surprising fact. It's even useful to do perturbation theory if the variation on the right-hand side is precisely zero. So that sounds strange. You could say, okay, if I already have a solution where delta m is zero, why should I care? Because we started this whole thing by saying that we are interested in having a solution where m is a little bit changed. And then we said, okay, to accommodate for the change on the right-hand side, on the matter side, we need to change the geometry a little bit. However, it's possible that we just change the geometry a little bit without changing the right-hand side at all. So in some way, we could also ask the question, even if this delta m is zero, is there a delta g such that the equation, the Einstein equation still holds, but there's a small perturbation on the geometry? And that's exactly the situation we have when we look at gravitational waves. It's similar to electromagnetic waves in electromagnetism. There you can think of these waves as just a perturbation of the vacuum where you have no waves. So you essentially solve the Maxwell equations and you find one solution is that the electric field is zero and the magnetic field is zero. And now a wave could be regarded as a small perturbation around zero here. And you have no, I mean, you could look at an electromagnetic field wave without the source. That's a valid solution. It's just an infinitely extended wave. And we can do the same in gravity theory. We can look at the wave without looking at the source. I mean, you know that we can study waves in electrodynamics without looking at the source. Of course, at some point, we also want to study the source. And that's exactly what people do who study now how these waves should look like. But we can also understand the propagation of waves to just look at the waves themselves without the source. And if you have no source, then this delta m is zero, but we still have a perturbation, a non-trivial perturbation delta g. Okay, so the example, I mean, it's maybe more than just an example, but it's an example of perturbation theory are gravitational waves. So what are we doing when we look at gravitational waves? So there, the given solution is usually just flat spacetime. We could also take another solution like the Schwarzschild solution and look how does a gravitational wave propagate within a potential of a star, for example. But let's not do that. Let's just study the simplest case where we say we already have a solution we already have the vacuum solution of Einstein's field equation, at least one, namely the one where we have flat spacetime. That's a possible solution. So this is eta, that's just a flat metric. I'm not very good at writing Greek letters, so this is the eta, that's the flat metric. And that's, of course, a solution of the Einstein field equations in the case where we have no matter. Now we look at perturbations around it. So in other words, what I want to do is to understand what is the curvature, or can it be that the curvature Rij in the perturbed case. So this was now what was before the G. And now for consistence with the exercises, which I will distribute next week, I will call the perturbation term, which we called before in general delta G, I'll call it H. It's just a name for it. So that's the small perturbation of the metric. Now, according to what we said before, when we linearize things, the curvature should, of course, still be almost like the curvature of the flat metric, which is zero. So that's just zero in our case, plus how it changes when we change the metric a little bit. So what I wrote down now is exactly the expression I already had before. In general, namely the one here that is underlined. So that's exactly the same thing. G is now eta and delta G is now H. And what we want in this case, because m is zero, we want this to be equal to delta m, to m, and this is anyway zero. So what you actually need to solve, so to solve therefore is the equation delta R eta H equal to 0. Of course, h equals 0 will be a solution, but that's a trivial solution. We are really interested in non-trivial solutions, such that in non-trivial solutions that can live on flat spacetime but have no matter term. Okay, now comes a calculation, and this calculation is a calculation that you better do yourself, because I don't think you learn much by looking at me how I do a calculation. It's a bit similar to, I mean, it's a rather mechanical calculation, because it's now just working with indices and so on, and we therefore decided to have this calculation as an exercise. I will now just summarize what will come out of this exercise, and next week, if you still have enough energy before Christmas to do exercises, you can solve this exercise and see all these claims that I'm now making. So the first thing to recall is that what I said before, that the curvature is, of course, or the Ricci curvature that we want to solve for. Maybe I should here still put the indices. We want delta Rij, this deviation, to be small. So the curvature is the Ricci curvature, which is a contraction of the Riemann curvature. And the Riemann curvature itself is something that depends on gamma symbols. I will now not write it down, on derivatives of gamma symbols, as well as on actually products of gamma symbols, and so on. So this is just to give you a flavor. And as I already mentioned before, the gamma symbols themselves involve the metric, so even the inverse metric in M, and then also derivatives of the metric. Now the idea is, or what you have to do, is to really explicitly write down this thing. So what, or this R. So what is this R? We said that this delta R is just the linear change of the curvature. And in this case, it's not only the change, it's a total curvature, because there was previously no curvature at all. So it's, you can see it as the curvature that you have when you have a very small deviation from the flat metric. And that you can calculate. So you just, what you have to do is you put into, so wherever you have the G, you put in eta plus H, where H is small and eta is the flat metric. And then you get an expression. I mean, you get a big expression, but you scratch all terms which are nonlinear. Of course, there will be nonlinear terms, because you see there's a product here of G's. And because each G has a plus H, there will also be an H squared and so on. But you just ignore all the square terms. And then you get an explicit expression for delta Rij for this thing. It's really just a rather mechanical calculation. It's actually still instructive to do it oneself, to just get a bit of practice. But as I said, I don't think you would learn much by seeing me doing it. I would just probably make a few mistakes, and otherwise you would not see much else. So what you obtain, however, is an expression which involves these H's. So this is just a symbol which means you, this is just the D'Alembert operator, which is defined by taking the derivative twice and summing over it. And you know that probably, and it will also be spelled out in the exercises. And then you have just different combinations of derivatives of H. Okay, actually it's a bit longer. So you get these combinations of derivatives of H. Yeah, I think it looks roughly like this. What is that? So that's maybe a strange thing. Here it's only an H that is derived, whereas the other things are just H's with indices. So for example, here, this just means you raise the first index of H, and then take the derivative. And this H here is just defined as H in N. So it's a trace of H. Okay, so that's some expression that you will derive. So that's the exercises. And of course, what we want, so what we want is again this thing. So that was what I called exclamation mark. We want to set the whole thing equal to the matter part, which is in this case 0. So we want this thing to be equal to 0. That's our requirement. Now there's one more thing that I should add here, namely that there is some degree of freedom. There's some gauge freedom that, and you're probably familiar with gauge freedom from electrodynamics. So the H, they're not all degrees of freedom of the H that are physically relevant. Why not? The reason is the following. So look at the coordinate transformation. So we could go to a new coordinate system where we just turn from coordinates to tilde coordinates by doing some little shift. So this just means the new coordinates, the tilde coordinates, are obtained by taking the old coordinates x and shifting it with a little psi. And psi is an arbitrary field, so the shift could be different at any place in space-time. Of course, it should be a continuous function, but that's just some vector field that defines a change. So that's just a way generically to change from one coordinate system into another. So you can define a new coordinate system in that way. That's all. It's just a slightly shifted coordinate system. But of course, if you shift the coordinate system, this will mean that also all these terms, the Hij's, will actually shift or be different. I mean, you know, if you change the coordinates, then the components of tensors change. So you have therefore a freedom. You can somehow change the components here by just going into another coordinate system. This doesn't change the physics at all. You're just choosing appropriate coordinates. So the gauge freedom that I mentioned before is essentially the freedom to choose an appropriate coordinate system. This is also something you can then do in the exercises. It will not be hard. It may look now difficult if I say it like that, but it turns out that you can find coordinates in which this expression becomes much simpler. So in the new coordinates, so choice of appropriate choice of this transformation, choice of psi of this vector field allows us to rewrite the expression above, the one with the one here, in a way which is extremely simple, namely it's just the D'Alembert operator of each component separately is equal to 0. That's now the new coordinates. And now you see we have a very remarkable result. The result is that it's possible to deterb the flat metric, which we started off with a little bit, by a little h, by a little change of the metric. But these changes have the form of waves. Of course, you know very well that the D'Alembert operator applied to some scalars. I mean, it's just an equation for any ij. So you take any ij and you apply the D'Alembert operator. The solution is, of course, a wave. A wave, by the way, that propagates with the velocity of light. That just comes from the fact that in the units we choose, the c was implicit. And so in this D'Alembert operator, you just have the derivative with respect to x0 and then with respect to x1 and so on. And if you would reinsert meters and seconds, there would of course be a c, which determines the velocity of these waves. So this expression tells you that there are little perturbations possible in space-time that still solve the Einstein field equations, and they correspond to the geometry propagating, or the deviations of the geometry propagating like waves. And that's what this expression here says. So indeed, it's true that the geometry, according to the Einstein field equation, or maybe I should put it like that, the Einstein field equation has the property that there are wave-type solutions of the geometry. And these wave-type solutions of the geometry are what we then see or observe as gravitational waves. Now, maybe I will next week at the beginning very briefly say a few things about why we can detect them. Maybe I should only say at the moment that it's actually really incredible, but true that we were able to detect them, because the objects, the sources of these waves are actually more than 1 billion light years away. So it's really a billion light years. So it's almost the same order of magnitude as the whole age of the universe. So it's something that during the whole age of the universe almost kind of traveled away with almost the speed of light, just to get the order of magnitude right. And we still receive a signal from it. So you can understand that this must be an enormously strong signal, something that we can receive from 1 billion light years, which was not directed towards us. It was just distributed in all directions, and we still receive it. So, and actually, if you look at the numbers, it's really, yeah, I would say, yeah, it's maybe beyond our imagination, because what happens there, the event that sends out the radiation of gravitational fields is in this particular case that was detected. So maybe you are all aware that in 2015, gravitational waves were actually detected in the LIGO experiment. And by the way, one of the honorary doctors of ETH was Kip Thorne, was the theorist who pushed this whole development and also got the Nobel Prize, apart from the honorary doctor of ETH. And he, I mean, so this detection was of an event that was 1 billion light years away, but it only lasted essentially, I think, a third of a second. But in this third of a second, the amount of energy that had to be dissipated was enormous. And the event that took place was actually the merger of two black holes. There were two black holes, each of the size of roughly 30 solar masses. So you can imagine like 30 solar masses, black holes merging. And within a third of a second, this whole thing essentially spiraled down and then merged into one black hole. And then there was a so-called ring down phase in which the black hole admitted again the spherical structure, and then everything was over after a third of a second. But within this third of a second, the energy that was dissipated is equivalent, I think, to, okay, I think it's roughly 3 solar masses, which is enormous. I mean, think of just in a third of a second burning 3 solar masses completely and dissipating it in terms of energy. That's just an incredible amount of energy. It's larger than all the observable light that we have in the universe. I mean, the power of all light that shines, of all the many stars we have, is weaker than that particular source at that point when it was merged. So that's why it's possible that we can detect that, despite the fact that it's so far away, that it's just an immense amount of energy that was burned in just a fraction of a second. Okay, this is just to give you some insight that when you now, these were all formulas and so on, but when you look why they are relevant, why we can actually make sense of them physically, then there are enormous time scales and length scales and mass scales involved. Okay, I think this is a good point to end today's lecture. As I said, I would maybe briefly then at the beginning of the next lesson tell you why we can measure that. What does it mean to have this changing, this let's say oscillating metric? Why is an oscillating metric even in some way having an impact on a device? What do you see in the device? How does it interact with the detection devices? Okay, I guess that's it for today. Let me just, for the last time, remind you to fill in the lecture evaluation. The deadline is tomorrow noon. And also tell you that next week I will do a more kind of speculative part of the whole lecture. So I will tell you a little bit about cosmology. I will tell you what the Big Bang has to do with the Einstein field equations. And then I will spend some time on explaining to you the so-called black hole information paradox, which is also a topic of current research and therefore in a sense quite speculative. Okay, thanks for staying and have a nice afternoon.